Welcome everybody to this little webinar about thermal remediation of LNAPL. On the front page here you see a couple of examples of NAPL as we encounter it when we do thermal. On the right there's LNAPL that came out at Edwards Air Force Base. On the left it's both DNAPL and LNAPL from the Young Rainy STAR project. And it's really interesting when we do these remediations. You know, sometimes we actually don't know if the chemicals come out as floaters or sinkers. We got both at Young Rainy STAR. At creosote sites, we sometimes see DNAPL turn into an LNAPL when it gets warm, and that means our oil water separator needs to work opposite, for instance. So thermal remediation of LNAPL is a little different than DNAPL, and that's what this is about today. Real quick, a little bit about myself. I did research on thermal remediation and tried to study the mechanisms that govern what happens in the ground. I did that in Oklahoma and then UC Berkeley later with Kent Udell and worked for Steam Tech for 4 or 5 years where we used steam in the field and did a bunch of the first ever types of remediations, a lot of them with LNAPL, some of them with DNAPL. And since 2004, 10 years ago, I've been with TerraTherm, and you can see there what my typical job description is. But I'm kind of a researcher from Denmark and started in the lab, wrote papers about this, tried to understand what was going on, and then now, luckily, I'm doing stuff in the field as well. One of the key big breakthroughs in thermal remediation was when the people you see up here on the top line got together and worked at the Visalia pole yard team. This was a huge creosote site in the late 90s that was remediated. It was a Superfund site, and 5 years after the thermal treatment, it was actually delisted and taken off the Superfund list by having been successfully remediated. It was just something that nobody thought could be done. And what the team did, Kent Udell, you see there, figured out basically with equations and students and papers how to do stuff below ground. And the Livermore team did a bunch of research and applications and did a big project at Livermore, the gas pads site, using both ERH and steam together to show how gasoline can be removed. And then Hank and Craig to the right from Steam Tech and Edison, the client, got together and with all their oil field experience transferred that to the environmental field. And you can see by some of the pictures down below Kern River where they've used steam for many, many decades to loosen up the oil. The pumps are different and everything, but that's where a lot of the expertise came from in the oil field. And you see the similarities between some oil field stuff and what we're doing when we're now doing in situ thermal. We learned a lot from those guys and use the same pumps and science that's behind selecting it and engineering and all those things. Visalia pole yard is shown in the slide, went down to 140 feet. It was DNAPL, but when it got heated, some of the NAPL actually turned into LNAPL and was extracted as such. A total of 160,000 gallons was removed, and you see those blue frac tanks in the foreground here. 4 of those were basically filled to capacity with what was called brown yucky stuff, which was the NAPL that came out. So a huge, huge breakthrough project, and as I said before, at the end, groundwater goals were actually met in the compliance wells, and the site was closed, and no further action was needed from that site. So when we're talking DNAPL, a lot of you have probably heard me before talk about these vaporization mechanisms. If it's TCE, PCE, the main thing that happens when you heat is that you turn up the vapor pressure and the Henry's law constant, and the little droplets of NAPL become gas and flow out with the steam that's generated. That's part of the process that happens for LNAPL too. For instance, if it's gasoline, the benzene and toluene and xylene will typically behave like that. but the majority of most LNAPLs is less volatile than that and needs to be addressed in a slightly different way. This slide shows you the main thing that happens to the liquid properties, and that is a viscosity reduction. And depending on how high the initial viscosity is, the reduction is more severe when you have a high starting viscosity. If you look at the upper left, the fuel oil starts with several hundred centipoise or centistoke viscosity, which is real sticky, like thick motor oil. And then when you heat it to near the boiling point, the viscosity drops to 10 or 20, and it's more like thick milk or something like that. Really a huge difference in viscosity when you heat things, and that applies to other NAPLs, as you can see in that kind of murky log plot there. But even heavy coal tar, for instance, can start to become relatively low viscosity when it gets hot. And what happens is you do extraction from sites that never really yielded any mass in the NAPL phase, and you start seeing it accumulate in your oil water separator, as you see on the right there. So you can basically start removing oil that wouldn't move before, or you can make oil that moved slowly come out much quicker in the liquid phase as well, not just the vaporization. So we have these three thermal in situ technologies, and the upper one, thermal conduction heating, where we are putting in the energy by heating steel rods and letting the conduction do the job. The middle one is electrical resistance heating, where we have electrodes in the ground and we apply voltage differences, and the soil heats up by the resistance. And in the bottom, steam injection, where you have actual screens in the permeable zones, and you make steam at the surface and you inject it. For many LNAPL sites, there's been a lot of steam applied, so the bottom solution here has kind of been a prime choice, and this webinar will focus quite a bit on that. But other sites, some of the sites can definitely be remediated with conduction heating or ERH as well. But a lot of the more permeable sites that have thick layers of LNAPL are pretty nicely attacked with steam, so there'll be a lot of focus on that in this talk. Here's an example of how steam moves across from an injection well, in this case one with 2 injection ports, and those are shown with little red lines. Over time, the steam grows from each of the injection screens, grows out and combines, and what happens with that is that there is a condensation front, which is where it's between the light and the dark here, and that's an extremely powerful mechanism for the steam to flow and displace the NAPL so that it runs kind of in front of the steam front here. And that's what makes this so different from conduction heating or ERH, that we actually have a convection component that is very strong and a displacement of the LNAPL towards the extraction well. It's exactly what they've been doing in the oil field for decades, but for remediation, it is extra important that you know exactly how this happens and at what rate the LNAPL is being displaced, so you can be ready to capture it when it arrives. Here's an example of a site in Pennsylvania where we used steam injection. We had some areas of the site with just 1 treatment interval and 1 of these injection wells, and other sites had 2 intervals with NAPL and solvents both above and below an aquitard, so we injected in both zones. We had to have fuel, of course, on site. We needed to rent a big boiler, and that's brought on site like this. And you can kind of in the background see the manifold piping necessary. Here's the layout from the site. A couple of different zones were targeted in different ways, and you can see where they overlap. We were treating both shallow and deep, and a very successful project where in addition to getting a bunch of solvents out, TCE and PCE, we had I think it was 70,000 pounds of LNAPL that was also present at the site, extracted, and a successful outcome. So that's what a typical steam site would look like on the surface. The spacing between these wells was around 40 feet, so quite a lot more than when you see an ISTD site or an ERH site where we have between 15 and 20 feet between the heaters or electrodes. So many, many fewer wells when you can actually use the steam successfully. Here's the first example of that I was involved in at Alameda Point. The red hexagon in each of those little corners, there was an injection well pair, and we were injecting outside in, and we were remediating a LNAPL zone with TCE in it, and the outside of it is shown by the blue punctuated line there. One extraction well in the middle and 6 injection well clusters around the outside. That was the approach. And real quick, in a cross section, you see those profiles. Those are laser-induced fluorescence profiles, and they indicate where the hydrocarbon signature was strong when we come down. We push down in the middle of the site. You see next to the blue extraction well, there was shallow contamination, and then you reach the water table, and right around the water table and below the water table, really high signals. So that's an LNAPL, kind of enhanced with starter solvents and with TCE, and it's been a little bit of tidal influence, and it's been smeared up and down, but it was present over about a 3 to 4 foot or 1 meter thickness, most of all the NAPL. We then injected steam at the top of the water table and down at the bottom at about 12 feet, right above the bay mud, which was kind of the bottom of the permeable formation. And I'll show you how the steam migrated in the next couple of slides. On the left, a plan view. On the right, a very schematic cross-section. We began injecting in the top because we didn't want the mass to just come off the water table and condense and then kind of deposit itself in this unsaturated zone. So we started by heating the Vados zone ahead of the deep zone. And then we kept doing that for a while. You see how the steam zones start to grow together. This is based on thermocouple data. We still haven't extracted any mass worth speaking of, just clean water at this point, 11 days in. Then around day 20, we started to see warm, hot water really in the middle extraction well and NAPL come out. You see the black stuff here. That's the first NAPL we extracted. And that was then preceded by when we were heating to near steam temperatures all the way to the middle. Recovery rate really peaked. Those little circles signify how many drums we filled with product, and this is product coming out as a liquid. We're up to 250 gallons after 27 days. Then we turned into the pressure cycling mode, where we were basically turning the steam up and down to get nice vaporization and depletion of the more volatile fraction of the NAPL. And we got another 250 or so total gallons out during that phase. We ended up with about 520 gallons in the drums, and 11 of them more or less filled to capacity with this stuff from one extraction well in the middle. Then we look at the dissolved concentrations, because it wasn't just the LNAPL we were after. The TCE, you see how it peaked around 5th of June, which is 20, 30 days in, and towards the end, the water was really, really, really low in concentration of all these things. We still had mass in the ground, but it was more the heavier TPH, as I'll show you in a minute. These are chromatograms of soils before on the left and after on the right. And you can see how the LNAPL has been depleted in all the more volatile fractions. From C16 or so 16 carbon atoms and smaller molecules have all been removed from the site. So all the BTEX is gone. Even the naphthalene has been reduced. That would be a C10 on this scale. And so by the steam stripping, just at the boiling point of water, we were able to remove a lot of this liquid NAPL, as you can see in the bottle, and we left the soil still dark and still with some TPH oil signature, but depleted in all the volatile components and more of a solid when it's been cooled off. The groundwater in a profile here, these are multi-level sample results. In the top, this was the TCE that was dominating the risk assessment at the site. You see how we had a really strong TCE plume, and at the end we were in micrograms per liter. Here we were pretty low, and a few years after this, when we went back out, we were basically a non-detect for TCE. So natural attenuation after the thermal took care of it at the end. So by knocking the TCE concentrations way down in the soils and in the groundwater, and then allowing a little bit of polishing by itself, we were able to basically take care of all the TCE at the site. One of the things we often get asked is, do you cause the DNAPL or the LNAPL to move to a different location when you do thermal? And here's an example of a data set to look for that. We repeated the LIF, laser-induced fluorescence survey, after and right next to the holes we used before. And the red profiles were before and the blue were after. So you can see that we haven't removed all the aromatics that actually respond to the LIF sensor. Those can be big carbon atoms like phenanthrene and stuff like that. But we've strongly reduced the signal, and in a couple of places we have actually smeared it down just a little bit. You can see PCO3 out to the right as a little indication that maybe by the steam we did, and by the pumping in the middle where we created a drawdown and then pulled the NAPL to the well, we might actually have, maybe 1 or 2 feet down. We may have a little higher signal than before, but that's a relatively small price to pay for getting your 520 gallons out of the ground and all of your TCE removed from the source area. So these are the lessons. Most of the mass came out as LNAPL when we talked about the oil. The TCE, though, came out mostly in the vapor phase. So you could see the difference in behavior there. More than 90% of the TCE came out in the vapor and was captured on charcoal, whereas the LNAPL came out as a liquid. And the pressure cycling was important. I didn't show a whole lot of that, but it was, especially for getting the TCE concentrations knocked down. So that would be the same if it was benzene and you had an LNAPL and you had strict criteria for benzene. You would definitely not forget to do the pressure cycling towards the end. Here's another much larger site, the Guadalupe sand dunes, and whether it's green or beige, whatever that color is, there was oil spilled from the surface. This is a deep oil field, and from tanks and from pipes they spilled, and then the oil had run down through the sand dunes and accumulated on the water table. Just one of the areas, the diluent tank area here, was 250 acres in size. We were asked to do a pilot test to see if steam-enhanced extraction would be effective. So when you drill down through this dune sand, it's just clean until you get to about 55 feet, and all of a sudden you start to see the capillary zone, and then boom, you hit the oil. This is a diluent type of oil mixed with crude oil. Diluent was used to mix the very sticky oil with, so it could easily be pumped to the refineries. And both of those two things, of course, were spilled together, and now occupies a zone right on top of the water table where it's trapped. Here's a depth profile down around the water table. You can see on the right what the soil cores look like, and on the left you basically see the TPH measured up to 10% by weight was oil in the highest concentrations here, so 100,000 milligram per kilogram. So a target right around the water table with extremely high concentrations. We did a pilot test like this. The inner square is the pilot test zone, and we had 4 injection wells surrounding the central extraction well. We then surrounded it by more extraction wells to keep hydraulic containment and to try to keep other oil from the outside flowing in and basically destroying the results in the middle square, because we wanted to compare concentrations before and after. So we needed to try to isolate the zone. So 4 injection wells, 9 extraction wells, with one of them kind of representing the middle and the real thermal treatment zone. Here's what it looked like. The insulated pipes go out to injection wells, and there's extraction wells in between, spacing with 70 feet between these. This is 50 feet, 55 feet deep target, so we could use a spacing of about 70 feet. And we had to build a temporary treatment system. You see the boiler there with a black stack, and in the white tent is the effluent treatment system. Here's a cross-section of the first phase where we used warm water flushing. We started just to see how much mass we could get out just with hot water. And this is a temperature profile showing that we're up around 80, 90 Celsius at this point. And basically, that didn't give us much mass removal at all, but that was to be expected. So, but if it had been effective, of course, it would be a much cheaper way to do the thermal remediation. We then turned the steam on and ran it for a while, and you can see in this picture how much hotter it got down in the treatment zone, and designated by those two lines, but also that the steam wanted to rise a lot in this formation. Above the water table, these are sand dunes, so these are wind-blown deposited sands and had very high vertical permeability. So one of our tricks here was not to inject so aggressively that all the steam would just migrate up to the surface and it would be wasted energy. And so we had to inject kind of carefully and then stop and have it not become too shallow. We also did pressure cycling here. I'll show the next picture of we turned the steam down, and then we have a little bit of shrinkage in the thermal zone, and we did that a lot to try to enhance the mass removal. Out of this field with one central extraction well that got surrounded by 4 injection wells, we ended up with 100,000 gallons of oil and LNAPL extracted. So that kind of tells you how high the concentrations are out there and how the technology can really mobilize at a lot of LNAPL mass when we need to. So in one day, for instance, we got 1,400 gallons, which would have been 3 times what we got at Alameda during the whole project. So the scale is very different, and there's a lot of oil that had to be taken off site for disposal. So this would have been 5 big frac tanks filled with product, so even more than the Visalia poly out of one extraction well. And here are the concentrations before and after. After are the purple ones, and you can see great reductions in some of the highest one. If you look to the left, where we're pretty close to an injection well on the inside of the target treatment zone, we're able to knock the concentration down maybe by 90% or so on average, but we didn't get everything. And there's always a little bit of a sticky, heavier boiling component of the oil that typically stays behind. Unless you have a really, really light LNAPL like gasoline, you can remove all of it, but not these mixes with crude oil, etc. And also a little bit of a downward trend that due to the drawdown that we did and the mobilization of the NAPL and its the Kona depression near the extraction wells, we did actually have a little bit of downward smearing of the LNAPL. Now the good news is it's not a DNAPL, so it's not an unstable situation. It's just a little bit of a vertical smear, if you will, caused by the thermal. So with 100,000 gallons removed out of that little area, of course it sounded very promising, but when you look at the bottom pictures, you can kind of understand the reason why this was not scaled up to the whole 250 acres. So if you imagine having to build what's on the right all over that area, it's an ecological, pristine area, and we would basically have destroyed most of that temporarily, and it would. And also the client did not want to pay for it, and they weren't forced by the regulators to do it, so it never went past this pilot test. But those are the reasons. So one of the things that's really interesting is at sites like this, when you get this much mass, why don't we use the energy in that mass to save on the fuel we use, for instance, for steam generation? And we do, and we plan to do that. Here's just a quick table of some of our projects where I've basically just done a balance, and the bottom line shows you there the fraction of energy in NAPL compared to how much we need. For Guadalupe, if we had used the 100,000 gallons, that would have covered 39% of the energy need to do the project. So it's getting up there with a significant fraction. If you imagine some refineries that have big spills and pools of NAPL underneath them, you can have sites that has more energy in the ground than it takes to do the thermal remediation. You can actually have, if you have permission to use the fuel that you recover, you don't have to buy any other fuel. You can run the process by what is in the ground. So an example of that, it's not just the energy savings and the sustainability aspect of it, but this is a traditional project. On the left you see the steam generator, on the right you see the process equipment. In this case there would be gas burned to make steam. There would be gas burned for a thermal oxidizer to burn the vapors and have them clean. Both of those, of course, it's just using gas. But what we're doing now in one of our big upcoming projects is what you see on this next slide, where we take the extracted vapors and the NAPL and we use it as fuel for steam generation. And the steam goes down in the ground. It carries the energy from the product extracted from the site and creates a huge benefit, less equipment and less fossil fuel used for the whole thing. Here's a quick balance for the site, preliminary estimate of how much we're going to extract, 13 million pounds. And if you look at the energy in that, most of that's going to come out as NAPL, and we'll have somewhere in the range of 240 million BTUs in NAPL. We need about 300,000 for the project, so it's close to all of the energy can come from the NAPL. The timing is not such that we have it on the surface to begin with, so we still need to use a lot of gas, but it's a $2 to $3 million savings just dollar-wise in fuel we don't have to buy when we have permission to use the energy that comes out of the ground. Of course, it has a big benefit for not just the price of the project, but for CO2 emissions and any sustainability aspects that would be looked at. So, a couple minutes left. Here's the final slide. When we do thermal remediation of LNAPL, it is simplified by the fact that the LNAPLs float on the water table. So finding it and delineating it is a little easier, a lot easier than DNAPL, and that makes it an easier target. Since some of these are in permeable zones, we've used steam quite frequently for LNAPLs, but we've also used ISTD, and ERH can definitely be used for it as well. Thermally enhanced free product recovery is basically an option where you just want to get as much mass out as possible, where you don't have to get complete removal and you can leave a little bit behind, but you've removed all the mobile mass. We call that GEFPR. That's another option. And of course, the liquid phase removal here is critical because the LNAPL, and especially when you use steam, gets displaced by the steam and needs to be pumped out of the extraction wells. And there's much more focus on that compared to when you're doing solvents, where everything vaporizes basically. So pressure cycling also is really a key to getting as much of the mass out as you can, both with respect to getting more LNAPL to come to the extraction wells, but also with respect to depleting the leftover mass in the volatile fraction. So that proper pressure cycling is really critical. And then the final point was the reuse of the produced NAPL. When you can get permission to do that, and you typically can, even though the first answer will be no, once you really get into it and talk more about what we're doing and how we're controlling emissions, no matter what, there's a huge benefit for some of the sites that has a large starting mass by doing that. So thank you very much for listening. I will now try to go and see if anybody has written me some questions and try to address those.